So welcome to this afternoon's session, which I have catchily titled Bringing the Performance of Structs to Java, sort of. I am still trying to find a better title for this presentation, I have to say. But essentially what I'm going to talk about is a project that we started at Azul, and I was going to say I've got Nitsan at the front here from Azul as well, which is about trying to improve the performance of Java applications. And that's something we're very concerned with at Azul, because that's our business, is creating Java virtual machines and trying to make them perform better. So this is something that we've been looking at in terms of basically a thing called ObjectLayout. And the idea behind this is to look at how native applications written in C and C++ have certain things that they use which perform better than Java. And thinking to ourselves, well, how can we take that and how can we replicate that in Java and make it get the same type of advantages? So if you look at the kind of things that we're trying to do here, it's about memory layout. So objects in Java get laid out in a specific way. If you look at C, it handles memory in a different way. If you look at C++, it deals with objects in a different way as well. So there's a quick show of hands here. Who's done some C programming in the past? Oh, okay, good. Right. So if I said to you struct, you know what I'm talking about. Great. Okay, so I won't have to explain a struct. But the key thing here is what we're looking for is speed for regular Java objects on the heap. And I'm going to say this several times during the presentation. It's all about speed for regular Java objects on the heap. Now, there are some things which we're not looking at doing specifically with this project. So one of them is we're not worried about improving footprint. We're not trying to compress data. We're not trying to make things fit into a smaller space. We're not worried about trying to do things so that we move outside of the heap space. Clearly, there are ways that we could do things if we did move off the heap, but we're not trying to do that. And we're not concerned about immutability. So we're not looking at using objects within Java which are immutable. Now, that said, there's nothing to say that if you have Java objects which are immutable, that you can't use the object layout project with them. But you're not restricted to only immutable objects. Now, if you look around, you'll find that there are some other sort of projects going on which might seem similar to what I'm talking about here in some ways. And if we look at how the goals of these projects overlap, we'll find that there are some relationships. So if you look at value types are something that are being proposed for JDK 10. And really value types are about allowing you to do certain things in Java that you can't do at the moment. So things like being able to return more than one value from a method without having to encapsulate them in an object, so a tuple in effect. Another thing that value objects is looking at is how to allow you to use a collection with a primitive type, because you can't do that at the moment. If you want a collection of ints, you have to wrap them in integers to make them objects, and then you can put them in a collection. So value types are about allowing you to do different things with respect of objects in Java and primitive types and how you can deal with those from a memory layout point of view. Now, in terms of the goals of that project, there is no overlap between that and what we're doing with object layout. Similarly, if you look at another project which is around the foreign function interface and a JNI, replacing that with a new way of doing things, which I have to say, having just written a bunch of JNI code in the last couple of weeks, it's probably something that will be very, very useful, and I would very much appreciate. But again, packed objects is what they're talking about there. There's no overlap in terms of the goals with this project. What we're focused on here is very much a different problem. Now, there is some overlap in terms of what the different things provide you. So if you look at packed objects, if you look at value types, if you look at object layout, there are some areas where they overlap. But it's kind of like if you said, well, okay, collections are similar. An array list and a hash map is a collection. They overlap in terms of the fact that they store things, but how they do it is very different. So we can use a Venn diagram to sort of represent the way that these three different projects overlap. And if we look at the more specific things around this, from the point of view of value types are about immutable objects. Remember I said that with object layout, it's not about forcing you to have immutable objects. So value types, because they are values, their value doesn't change, so it's immutable. It's about, as I said, return values. If you want to return tuples from a method, then you can use a value type. You can use them either on the heap, or you can use them on the stack. So they're very flexible in that respect. If you want to use value types when they're delivered into Java at some point, then you will need to write new code. So you'll have to change some of the code that you use in order to use value types. If we look at packed objects and foreign function interface, this is a different sort of thing. So this is actually about dealing with things off the heap. We're dealing with a way of communicating with native code, with data which might be stored outside of the heap. It's about sharing data between that native code and the Java code. And it's also about having very precise control of the layout of the data. So a good example there is if you've got some native code which is reading data from a network and you get TCP packets. TCP packets have a well-defined format, and so what you're representing in memory has to have a very well-defined format. So that's what we're talking about in terms of precise layout control. Again, if you want to use that when it's available, you will need to write new code. So you need to modify your code in order to use it. Object layout. Well, as I've already said, and I'm going to say again, it's about speed for regular Java objects on the heap. So the idea is that you won't actually have to really modify anything in your code. Now, that's not strictly speaking true. What we're dealing with here is objects being usable by all existing code. And I'll kind of make that clearer as we go through and we look at some of the examples in terms of how you can deal with objects and have them work in exactly the same way. There are a couple of places where you do need to modify the code slightly, but again, I'll kind of address that. And then there is, obviously in our Venn diagram, an area where there's a very small sort of overlap where you might have an array of small footprint values, and then you could use all three of these things at the same time. So where did the idea of object layout come about? Well, my boss, Gil Tene, he was having a discussion with Martin Thompson, and they were talking about how to improve speed in Java. And they said, we need structs in Java, because people often try to actually replicate the way structs work in native languages in Java. And they do this in various ways, which are not really the best idea in terms of code safety. So a lot of ways that people have tried to do this is using things like sunmisc unsafe. Now, sunmisc unsafe is one of my favorite APIs because I just love the idea that you've got this class called unsafe. There's a clue in the name there as to whether you should use it or not. So, people do use it, but it's not really supposed to be used by people outside of the JDK. And that begins in JDK 9, which is a whole other story anyway. And if you look at structs, everybody gets those for free in C and C++. They're just there. They're part of the language. We've all used them. We know what they are. And so why can't we have that kind of thing in Java? And the answer is, well, yes, we already have structs in Java. If you think about it, they're called objects. There's a lot of similarity between a struct and an object. A struct is just a way of grouping together pieces of data, which might be the same type or same primitive values or primitive types, or they might be different. But it's a way of grouping things together so we can treat them as a unit. So that's what an object does. An object allows us to encapsulate data so that we can treat it as a unit. What we need to do in Java is figure out how can we get the same speed that you get with structs by using objects, because although they're similar in terms of what they allow you to do, they're not actually the same. Certainly not the same in terms of the implementation underneath. And it's all about capturing the enabling semantic limitations. And what that really means is how can we use Java as we know it without really having to introduce, well, certainly any new syntax, maybe some new APIs, and allow us to do the same thing that we can do with structs. So the question that we need to start with is, where does the speed come from? if I use a struct in C, and I'm going to use C now rather than saying C and C++, just to make life easier. But when I say C, think of it C or C++. So where do we get the benefits in terms of speed in C? Well, there's two things that we can do with the layout of structs that gives us speed. One is dead reckoning, and the other is streaming over arrays of structs. So let's look at those in a bit more detail. If we want to group together some data in C, we might do it this way. Let's say I want to create a struct which represents a square. So a square is going to have two ints which represent the x and the y coordinates of one of the corners. And then I'm going to have another int which represents the size. I put that in a struct, and I've got my three values all grouped together. If I then create one of these and push it onto the stack, what I'm going to see in memory is something like what we see in the diagram. So we've got three ints on the stack which represent x, y, and size. And the struct really treats those as a single piece of data. Even though it's three different values, it's treated as a single piece of data. Now, if I want to create an array of these, because I'm using C, I can't simply instantiate objects. I have to allocate memory explicitly. So I can use malloc to do that, and I can say, give me a piece of memory which will hold at least 5 square structs. That gives me a pointer, an explicit pointer into memory, which allows me to say, right, that's the beginning of the area of memory. And then what I can do is I can lay out the information as we see it there. So we've got 5 structs, all of which have 3 values associated with them. Let's say I want to go to one of the pieces of data in that array. And so what I actually want to go is I want to go to the 4th element in the array, which I call element 3, because being computer scientists, we start counting from 0 rather than human beings, which count from 1. Well, unless you're a Pascal programmer, and then you do start counting from 1. But you start from 0, and you say, OK, I want to go to the 4th element in that array, and I want to get the y value associated with that. How do I get to that piece of data? And the answer is that I can do it mathematically. I can say, OK, I know the beginning of the array, because I've got the address of the array, explicit pointer. I can then increment that by 3 times the size of my struct. And that will give me the beginning of the 4th element in the array. And then in order to get to the y piece of data, I simply add size of int to that, and that will give me the address of the y value associated with the 4th element in the array. The nice thing about that is it is simply a mathematical calculation. It's dead reckoning because we can take the address of the array and we can calculate simply and very quickly where that piece of data is. The other thing that's very good in terms of this is that if we have an array of squares, we know how big they are. And typically what we like to do with data that's stored in arrays is we like to iterate over it. We want to go through and we want to search, we want to sort, we want to do something with the data. So we might start with the beginning of our array and look at the first element of that array. Then we want to look at the next element. So we simply say add the size of the struct, and that gives us the address of that. So we're using dead reckoning to get to the next one. And we can repeat that for the second one, the third one, by just incrementing by the size or the number of times the size of the struct in order to get to the beginning of the struct that we're interested in. The key thing about this is that that will give us very good performance. Why it gives us very good performance is that the hardware underneath now is so sophisticated that it's going to start noticing that we are accessing memory at a particular increment repeatedly. So we're going struct plus 1 times struct plus 2 times struct, and so on. And so the underlying hardware is actually going to start doing prefetching for us. It's going to notice the way that we're doing our memory accesses, and it's going to go, right, you're probably going to want the next element in an array. So we'll load it in advance so that when you request it, it's already there. We get better use of the cache, we get better use of the memory bandwidth, and so we get better performance in terms of accessing that array. And as we start going through it, we'll find that it'll warm up and we'll get better performance. So let's look at how we do that in Java. Same thing that we want to do. So this time we want to have a square, but rather than being a struct, we're going to call it a class. So we're going to create an object which is of type square. Again, the class encapsulates the data, so we have 3 ints, x, y, and size, same as we had before. And we can instantiate one of those and create a new square. That looks very similar to what we had before, but it's not quite the same. Now we have an object, and an object is more than just those 3 pieces of data. There's an object header, there might be methods associated with it, there might be other pieces of data and so on, but it's going to be slightly bigger than just our 3 integers that represent the data. So that's looking at just the object itself. What happens when we start creating an array of these things? Well, we're dealing with the heap. So objects are allocated in the heap rather than being allocated by doing a malloc. If we do that, what's going to happen is, if we're very lucky, we will get all of those squares allocated sequentially in memory, so they'll be contiguous in memory. I say if we're very lucky because we may be using multiple threads to do the allocation. We may have thread local allocation blocks associated with those threads, which will be using different parts of the young generation. So they may be allocated in different thread local allocation blocks, and so they won't be contiguous. So if we're lucky, we'll get them allocated contiguously in memory. So we could theoretically use dead reckoning, and we could get benefits when we iterate over them. But what happens when we do garbage collection? Well, garbage collection is going to start moving objects around. It's going to move objects from the young generation to the old generation. There may be objects moved around within the old generation when it does compaction, and things will not stay the same. So we end up with this situation where the squares get moved around, and so we don't have them contiguous in memory. Things could get more complicated because the array that we have of our squares is mutable. Let's say I want to change one of those references. So I can move, let's say, square 4 to be a different one, which is going to be at a different place in memory. So again, no guarantee that it will be contiguous with the data that we already have. And things even get more complicated because in Java, because it's an object-oriented language, we have the idea of inheritance, which means that anything, if we want to store a square there, it doesn't mean it has to be a square. It could be a subclass of square. So I could create a new class called filled square, which has some extra information in it. Bigger object, we allocate that, we store it in one of the references in our array, and it's a different size. So we're not going to have contiguous data, we're not necessarily going to have the same sized objects. And the key thing here is to understand that we're in a situation where we can't guarantee that the data will be contiguous in memory. Like I say, there might be situations where it will be, but we can't guarantee that from the point of view of the way things are actually laid out, and if we wanted to then take advantage of some of these things. So, in effect, what we're dealing with here is 2 different things. In C, if we look at structs and an array of them, what we have is an immutable array, because we can't actually change the array. We've allocated memory we've allocated memory using malloc, and that memory is fixed in terms of how we use it. So it's an immutable array of exact same size structures, because we can't change the references that we're storing in there. We simply have structures laid out sequentially. In Java, what we're dealing with is different. We're dealing with a mutable array, because we can change the references that are stored in that array to different objects of a different type, which could be a subclass, and of the same base type objects. So they don't have to be the same objects. As I say, we could use subclasses, doesn't matter. So this is where the object layout comes into actually what are we trying to do. And the idea behind this project is to address 3 different sort of situations where you might use this type of struct, if you like. So the first is having an array of structures. Second one is very common, where we have a struct which has a struct within it. So nested structures. And then the third one, again, which is very common, is the idea of having a struct which has an array at the end of it where we might want to store some data. So how can we deal with these three situations, which are very common in C and very common in Java in terms of the actual data that we're going to try to store, and express those in Java, which we can obviously do, but how do we match the speed that we would get using a struct rather than an object? Now, the idea behind this project is to do the same thing that was done with the concurrency utilities back in Java SE 5. Because if you go back to before Java SE 5, writing multi-threaded code was very difficult. You literally had 4 methods from the thread class, which were sleep, wait, interrupt, and notify, which allowed you to coordinate different threads and be able to coordinate their actions. Along came Doug Lee and a group of other people and decided that what was needed was a better set of libraries. And so they wrote the concurrency utilities. They wrote them outside of the JDK. So they created a set of libraries as a normal Java library without having to change any of the syntax of the language. So it was simply a jar file that you could use and would give you things like semaphores, it would give you atomic operations, mutexes, and so on. And the way that did, or the way that worked, was to use all of the existing Java syntax and to use all of the existing capabilities that were there. And if you look at something like an atomic long compare and set, you can implement that perfectly well using synchronized. So you can use synchronized block, synchronized method, and you can implement an atomic long compare and set. But once that got moved into the JDK in Java SE 5, suddenly the JVM could know about the libraries. So it knew that these libraries existed. The JVM could then take advantage of its knowledge of these libraries to improve the efficiency of them. So if you look at an atomic long compare and set, and what the JVM can do with it, rather than using just standard Java code, the JDK can say, right, I know about atomic long compare and set, I'll use a single x86 instruction to do that. So suddenly it gets much, much better performance. So the idea of the ObjectLayout project is to do the same thing. We create a library outside of the JDK. We use just standard Java to write the library. Then when it gets moved into the JDK, we can optimize it from the JVM perspective. We can intrinsify operations in terms of the library and get better performance. Let's look at the first of these situations then. So as an array of structs. Now the way that this works is that we introduce a new class. We introduce the structured array. So obviously it's named to indicate what it is. It's a generic collection, so it has a type associated with it. And what it is a collection of object instances of an arbitrary type. So any type that we want to store in there, we can. But it is a collection of exact types. So this is where we get around the problem of not being able to put a filled square in an array of squares. So what we're saying is that you can store squares in this structured array, but you can't then change something to be a subclass of what it is you're storing. So it very much captures the idea of an array of structures. So it's this immutable array of exact same types. It is arranged like an array. So there's a get method associated with it, which takes a value, which is the index, and will return you the element that's stored at that index. Because it's immutable, it has to be immutable in order so that we can't replace elements, so we can avoid the problem of objects moving within the heap because we've changed the reference to something else, something in a different place, changing object reference to something which is a subtype. So it has to be immutable. We can't replace any elements. So we say, okay, it has a get method, so we can retrieve them, but there's no put method because we don't want to let people change the references in that array. Now, in terms of creating one of these, you have to use a factory method. So you use structured array, new instance, and then you pass in the type of the object that you want that array to, structured array to hold. So you pass in some class.class to give it the reference, and then the size of the array that you want to create. And what that will do is it will instantiate all of the elements that you need at instantiation time of the structured array. So in the same way that if you create an array of structs in C, it's going to create an array of objects for you, and all of those will be created at the same time and placed into this structured array. So they're immutable, they're placed in there, and then they're ready to use. Now, when I say they're immutable, the references to them are immutable. The objects themselves do not have to be immutable. So you can put a square in there, and you can change the values associated with that square. You just can't change the reference from the structured array to that particular square. In order to make your life easier, it does support the idea of arbitrary constructor and arguments for the members of the structured array. Because quite often, when you create objects that you want to store in a collection, you need to pass specific arguments to the constructor of that object. So we need some way to be able to do that with the structured array. And the way we do that is through a thing called ctor and args, which is just, I guess, a shorthand for constructor and args. So let's look at how that works. Let's take a very simple example. I have a class called foo, and that has a private variable, which is the index. So what I'm going to do is I'm going to store a value, which is the index of that object in the structured array. And so the constructor will take a long, which is the index. So when I construct my structured array, I want to be able to pass in the index as those objects are constructed and populate the structured array. So the way we do that is to first of all find the right constructor of the foo class. So we use reflection, we say get the constructor of the class, one that is of type long, single argument, so that matches the constructor we have in our class, and that gives us a reference to the constructor. What we then do is we use the factory method to say, in this case, we want to create objects of foo.class. We're going to make it of size 8, but then we're also going to pass in a third argument, which is the constructor and args provider. And the constructor and args provider is a functional interface. So it's an interface that has one abstract method, so we can use a lambda expression to represent that. So here what we're saying is that the way that we want to use that constructor is use a lambda expression where the variable that gets passed is the context. That's the context as the object is created to populate the structured array. And then we can call new constructor and args of type foo, so it's going to use the constructor that we've got by passing it in there, and it's going to use the context getIndex. So we'll get the index of that object in order to pass that as a parameter to the constructor and create the objects that populate the structured array. So all the way through the 8 objects that we create, the index will be passed into the constructor as they're created. Obviously, if you want to do more complex things, then you can do that. It's very easy to change the way that constructor and args provider works, and you can simply do whatever you need in terms of constructing the objects that you want to put into the structured array. So, one of the things that was examined in terms of a structured array was how to deal with the liveness of objects. And the initial approach that was taken to this was to say, well, if you have a reference to an element in the structured array from anywhere else in the program, then that will keep the structured array alive. And if you think about it, that's what happens in other runtimes. So if you think about an array of structs, if you've got an array of structs, then you can't free it up until you no longer have use of any of the structs in that array. Once you've stopped using all of the elements in that array, then you can free the memory up. But you can't do that until you've stopped using all of the objects or all of the structs. So in essence, that array is kept alive whenever there's use for any of the elements within it. So the same kind of idea was taken in terms of a structured array. But then a bit more thought went into that, and people said, well, hang on, objects within this structured array have real liveness. Unlike in C, which doesn't have a garbage collector, Java already has a garbage collector which tracks reference to objects. So we know when we've got references to objects which are in the structured array, we know when we have reference to the structured array. Why don't we make use of that? And so that's the way that things work in the current prototype. So we say that a structured array is just a regular collection. It's a thing that allows us to put a group of objects in it. We just have certain constraints on that collection in terms of not being able to change the references, not being able to change the types to subtypes, and so on. So a collection keeps its members alive. If we have a reference to the structured array, all of the objects that are referenced by that are by definition still live, because there's a reference from something that has a reference to it. But the collection members don't implicitly keep the collection itself alive. So if I do away with all the references to the structured array, but I've passed a reference to one of the objects in that structured array somewhere else in the program, and I've still got a reference to that single object, that object will not keep the structured array alive. So at that point, the garbage collector could say, there are no references to the structured array, that can be garbage collected. There are no references to any of the objects referenced by that structured array, except for that one that you've got a reference to from over here. All of those other objects can be garbage collected. So it works in exactly the same way as any other collection works. And you can think of it like the collection is a collection of plain old Java objects. So it's regular Java objects, speed, regular Java objects on the heap. Now, in terms of the features of a structured array, first is that we realize that this is 2016, so the indexes into the array are going to be longs, not ints. We realize that some people like to have big arrays, so we'll use a long. Makes sense. Nested arrays are supported. You can have multi-dimensional arrays, you can have composable arrays, all of that will work. So you can have a structured array which contains elements which are structured arrays. And then they can have elements which are other objects. So there's no problem with doing that because a structured array is just a Java object. You can store it anywhere that you can store any other Java object. So there's no difference from that point of view. A structured array is subclassable. So we think that there are a number of places where people might want to subclass a structured array and use it in particular ways. So we want it to be subclassable. We want people to be able to take subclasses of it and use them. A structured array is not constructible. So we've seen already that we use these factory methods. So the idea is that you cannot construct a structured array using a constructor. You must create it with a factory method. Does anybody spot the contradiction in what I've just said? Very good. Yes. You can't, theoretically, so you can't have something that's subclassable but doesn't have a public constructor. Because if you want it to be subclassable, it must have a public constructor. So we're stuck with a little bit of a problem here. If we want our structured array to be subclassable, but we don't want it to have a public constructor, how do we do that? So Gil, my boss, went away and he came up with an answer. He said, we will use constructor magic. So it's like, okay, what's constructor magic? Constructor magic says that we will have a public constructor for the structured array. But the constructor will take an argument which is a context. And the context will allow us to determine where the constructor is being called from. If the constructor is being called from the factory method of the structured array class, then we will allow it to be constructed. If the context shows that we are calling the constructor from outside of the structured array, then we'll throw an exception. We'll say, no, we won't allow you to construct this object. So it's kind of a way around it. So there is still a public constructor there because it has to be, but you can't call it and actually create an object. It will throw an exception if you do it outside of the factory method.
But then how can the subclass call it?
Oh, well, because a subclass can call it by doing a super. That's not a problem.
Wouldn't that throw?
No, because it knows the context of where it's being called from. As long as it's called from the factory method, then the context will identify where it's being called from. So that will work, yes.
Because
So then we need to understand how we can optimize this. 16 minutes, okay. So what we introduce here is a new heap concept. So this is separate from the code that you're looking at. It's how the JVM actually deals with these things internally. We introduce the idea of contained and container objects. So we know that we keep references to objects through the garbage collector. What we now have is the ability for a collection to say that it has objects which are contained by it. So there's a reference which says this object is contained by this collection. And what that allows you to do is for the JVM to say, okay, this object is contained in a collection, and it can then get a reference to the container of that object. So it's a way of tracking the parent, if you like, of the collector or the collection. It's a way of tracking the collection so you can find out what thing is containing this particular object. That way, if the garbage collector comes along and says, right, I want to move this object, it says, oh, it's a contained object. So it says, right, give me the container of this object, and then rather than just moving that one object, it can go to the container, move the container and all the objects associated with it as a single unit. So it can keep everything together in contiguous memory, and that way we can avoid problems of things getting broken up. So we effectively treat it as a single object, even though it's made up of several smaller objects. This is very simple to implement. We've done it through the OpenJDK. We've done it through our own Zing collector, and so you can find more details about the algorithm on the website, which I'll show you a little bit later on. So how do we get the benefits of this? Well, the streaming benefits come directly from the layout. If we make sure that everything is contiguous in memory, then it doesn't matter from the point of view of the JVM. As soon as we start referencing objects by doing a certain stride, the underlying hardware, the caching hardware will notice that, we'll start doing prefetching, and we'll get the same benefits we would with an array of structs. Dead reckoning is a little bit more complex because we don't have to do any dereferencing by following links between objects, but we do have to take into account a few extra things because we're dealing with objects rather than structs, so there's an object header involved, so there's a little bit more sizing of the object that we need to work out in order to figure out the address of a particular element within the, or particular piece of data within the array. But it's certainly possible, it just takes a little bit more type of work. So let's look at the other two things that we're dealing with here. One is the idea of a struct with a struct inside, the other is a struct with an array at the end. So again, going back to looking at how we do these things in C, this is where we'd have a struct within a struct. So I'm going to create a line which has two structs which are endpoint 1, endpoint 2. They both have an x and a y value which are ints, and so again, in terms of the memory, we'll see that we have a stack where we've got int x, int y, int x, int y on the stack. Effectively, they're treated as two separate collections of data, which are the endpoints, and then that is in itself treated as a single collection of data, which is our line. Great. If we look at that in Java, obviously things are a little bit different, because in Java, we can create a class where we've got references to endpoint 1 and endpoint 2, which are two new point objects, but these are implicit pointers, not explicit pointers. And implicit pointers in this case gives us a reference to another object. And we know that that reference to an object could be anywhere. So it's not actually the information being placed inside the struct or the class in this case. They point off to other objects. So if we want to create one of these things where we want to actually treat this as a single object, we need to do a little bit slightly more complex code. So now what we need to do is we need to say that in the case of our line, we're going to create an endpoint, but we'll label it with an annotation, say that it's intrinsic, which means we're going to treat this as the same part of, or part of the same object in essence. And so we create an endpoint, but now we're going to use the intrinsic object, which is another part of the object layout library, and we'll call the constructor within method to say, in this case, use the method handle lookup, because we need a reference to the method handle. So we'll use the method handle lookup. We'll say that this is going to be called endpoint1, and we'll refer the link for this object to be this. So we're linking it to this particular object. So what then the JVM will then say, okay, this will be in effect intrinsic to this object. So we treat the fact that we've got the line and endpoint 1 and endpoint 2 all as a single unit of data. Now, from the point of view of the Java code, nothing changes. We still have a reference to endpoint 1, we still have a reference to endpoint 2. And so we can follow those in exactly the same way that we do with other object references. We can use them in exactly the same way. No code changes required for that. Still implicit pointer. Only thing that's a bit tricky with this is that we have to survive reflection overwrites, because reflection allows you to do some stuff which is a little bit kind of messy. As long as you're not using reflection, none of these problems exist, so we don't need to worry about it. What's that?
Or unsafe.
Or unsafe, yes. Yes, if you don't, but it's unsafe, so we won't use it. So this is what it looks like. So we still have our class with two endpoint references, but now rather than just pointing off to somewhere randomly in, well, not randomly, but 2 points that are distributed somewhere in our heap, what we do is we get the virtual machine to allocate the memory and place it directly next to the line object. So we've still got our references to point and point. They're still outside of the line object, but we can treat it all as a single unit of data. And then as we need to move it around, we can move it around as one unit of data. We can also have it contiguous in memory, so again we get this ability to do dead reckoning, because we don't need to follow the reference from endpoint 1 to the object, because we know it's immediately after this object, so we can calculate its position and have it done directly within the JVM. If we look at a struct with an array at the end, what we use for this is another set of classes which are part of the part of the object layout library. And what this does is it has things like primitive long array, primitive double array, so that we can say these things are going to be in our object, and by using those, again, the virtual machine can intrinsify those and say, okay, you're going to have an array which is sitting at the end of this object. So we'll take that reference, so it's still a reference that we can use in exactly the same way as we can with any other Java code, but we'll position it at the end contiguously with that object. And so it sits at the end of the object, and we have no problem with doing that. So you've got all of the primitive long, primitive int, primitive double, and so on, and there's also primitive reference array, which allows you to reference an array of objects if you wanted to. Structured array is also subclassable, captures structured with array of structs at the end. So you can put a structured array as an array at the end of your object if you want to. And the nice thing about this is they're all composable. So we can actually get to the situation where we have, sort of a fractal type of approach to what we're dealing with. So we can start off with our heap space. We can create within that a structured array, which has a structured array of type foo associated with it. So we've got structured array of structured arrays. Foo so that gives us our structured array of foos as the elements within that structured array. Foo itself could then have an intrinsic bar, an intrinsic baz, so that's like our endpoint 1, endpoint 2. So those will be contiguous in memory. And then you could also have a structured array at the end of that of type mu, which we'll say is of length 4. So all of that is going to be treated as a single piece of data within the heap. And so it will be moved around as a single element. Now, clearly, depending on how big you make these things, that may have an impact on how the garbage collector works, because certainly in terms of allocation, because you may find that if you create a very big structured array initially, it will automatically be allocated in the old generation rather than in the new generation. But it doesn't actually affect the way it works. Status-wise, there is code available for this project available on GitHub. So you can go to objectlayout.org and follow the link from there. It is fairly mature semantically. As Gil likes to say, he's still trying to work out the spelling. So we may change some of the names of the classes, but essentially, we're still, we've got a good working set there. We have done, at Azul, we've done intrinsified implementations for OpenJDK. We've done intrinsified implementations for Zing. And some of the performance numbers that we've done look pretty good in terms of what we're doing. So we've tried implementing HashMap with the get operation, and we get about a 6% improvement in performance by using this. So that's the kind of thing that can be quite significant if you're doing a lot of HashMap type of operations. Next steps for us is to move this into the JDK. So we need to do things like get a JEP, JDK enhancement proposal going. We're very proud at Azul of the fact that we have now finally got a JEP accepted. It goes into JDK 9. So that's the, was it on spin wait? What's it called at the moment? Yes, on spin wait. So it's a very small change, but it means that the JEP process does work if you're outside of Oracle, because we've managed to do it, even though it took a long time. So the other thing that's quite interesting is, can we intrinsify code? And I was talking to Nitzan about this morning. Can we intrinsify code without changing anything? So can we get the JVM to actually start noticing that you have objects which could be treated, or get the compiler to look at it and then figure out that these objects could be treated as a single element of data and do it transparently from your code? You don't actually have to change any of the code. It will figure it out for you. That's a bigger project. We haven't quite got there yet. Yeah, and then obviously we need to get object layout into the Java SE specification, and then we need to get the JDK to improve performance by intrinsifying what's actually going on underneath. So just to summarize then, a whole bunch of new classes in org.objectLayout. Proposal, as I say, is to move them into the namespace Java SE 10 at some point, so we can get the improvement in performance, but without having to break any of the language changes before that. Works out of the box on Java 7, 8, and 9. Reason we can't do it before 7 is because we need method handles, so we can't do it on Java SE 6, for example. No syntax changes in terms of the language, no bytecode changes, so it's transparent from that point of view. It's just a set of libraries, few changes in terms of the way you use the code, so on. No new required behavior from the JVM, so it will run on a JVM that doesn't know anything about the object layout library, and then it can go fast on JVMs that do know about the object layout library. So that's the benefit of this, is that you can start off with just using any JVM, and then we can move to a better performant JVM without changing any code. So I've got 3 minutes left, so if anybody's got any other questions, I see a question straight away at the back there.
You said that object that contain intrinsic objects, its whole set of objects is viewed by VM as a single piece.
Yes.
And what if sub-object is leaf and parent object is dead?
So hang on, if some object is a leaf.
Live.
Oh, live.
Sorry.
Okay. So if you're saying that if you had objects which were, you had references and then you dispose of a reference so that you could garbage collect that one. Yeah, yeah, I mean, well, I suppose there's two things that we could do there, and that's up to the JVM, because from the point of view of your code, nothing changes. But we're left with a couple of options in terms of JVM. JVM could either just say, well, okay, depending on how much space that wastes, we could just leave the object there and not garbage collect it. So it becomes kind of like dead space in our bigger object. Or if it says, well, okay, we really need to, in effect, garbage collect, do garbage collect it, you could actually compact the remaining data. But I would have to say that in a situation like this, we're not really looking at, this is not really targeted at situations like that. It is targeted more at situations like where you have a line where you've got two endpoints, and so they're immutable, meaning you're not going to lose a reference to one of the ends of the line.
And what if I lose the reference to the line by...
Oh, well, if you lose a reference to... Yeah.
What's called a reference to the one of the endpoints in other data structure?
Oh, that's fine. That's fine, because, again, it's the contained and container reference. or relationship. So if you stop referring to the line, but you've still got a reference to one of the endpoints, the garbage collector will just collect the line object and the other endpoint, but it will leave the live one still there. So that will still be quite valid. There's no problem with that. Yeah, that will work quite happily.
Do you have any thoughts about the type safety, especially with regards to calling a constructor with arguments and generics, for example? If you pass generic arguments, say, possibly even non-generic, then you might have problems there.
Well, there should be no issue at all, because if you think about it, what you're storing in the structured array is just a Java object. So whatever applies to the constructor of a Java object is going to be the same rules that apply to whatever you store in a structured array.
As in, you're calling the constructor by reflection, right?
Oh, I see. Right.
So the arguments you pass to the constructor aren't type safe, essentially, because you're just passing, like you had the lambda where you got the context, then you say
Yes. Yeah. So you get
plus essentially an array of objects.
Yes.
And that's not type safe.
I would have to think about that one a bit more. Yeah, I have to think about that one to see if I can come up with an example where I think that wouldn't work. But yeah, we'll take that offline. Does anybody else have a question? Yeah, front.
Two related things. Firstly, you didn't say very much about the motivation for doing it. Secondly, you gave the hash map, or you only gave a very brief thing about speed. Surely something like iterating through a list of points would be.
Okay, so to take those very quickly, because I'm actually out of time now. So the one motivation is because we want to make Java go faster. You know, that's our business. We do JVMs, so we're looking at ways to improve the speed of Java. If we can do that through improving our JVM and ultimately the OpenJDK, that's all good. So that's part of that's our motivation. Second thing is, yeah, I mean, we should come up with more like proof points in terms of performance. We just haven't done that yet. So, I mean, it's still fairly early in terms of this project at the moment. So, yeah, expect to see more. I mean, if you have a look on the website, I think there might be some more details on there. Okay, I'm going to call it a day there. So thank you very much.